All right, guys, we're looking at Math 8, Day 6. So we should have just gone over a review, which we didn't have a video for, but we should be going over those in class. Obviously, Math Lab's available if you guys have extra help. So today we're going over lesson 41, 42, and 43. And just talking about those, doing some examples. We're still kind of, we're still not using calculators, but we are still kind of advancing at a little quicker pace than we will be later on in the years, just because a lot of this is still heavily review through the vocab and things like that. Hopefully it's coming back to us pretty quickly. If not, we get into Math Lab. We'll help you out. We'll get you squared away and make sure it's all making sense. And again, we're not rushing through it, just assuming that you got it down. We still want to make sure we're taking our time on it. It's just this will allow us more time down the road to get to some of the more difficult concepts. Okay, lesson 41, the concept we're looking at, the new concept is functions. We looked at functions last year. Again, if you've graphed a line and a coordinate plane, then you are familiar with what a function is. So a function is a mathematical rule that identifies a relationship between two sets of number. A function's rule is applied to an input number to generate an output. For each input number, there is one and only one output number. So if we're to graph a function, whether it's linear, quadratic, whatever, it's going to pass the vertical line test. So if we ever have a graph where it doesn't pass the vertical line test, then it's not a function. So again, not the best artist on that thing, but let's say we have a function. This is our coordinate plane, my y-axis, this is my x-axis, and we have something like this. Well, then I draw a vertical line and it crosses in 2 points. Well, that means we would have one input and two outputs. It would not be a function. Okay. Again, our input is our independent variable. That would be our x, and then our y is our dependent variable, our output. So whatever we put in for x, let's say our function is y equals 2x. Okay, well, I put in 0 for x, then my y is 0. I put in 1 for x. 1 times 2 is 2. 2, 4, 3, 6. So whatever comes out here is dependent upon whatever I put in here. So input, independent variable, dependent is my output. So sometimes we'll say independent variables. So usually we call it our x and y because that's how we graph it on coordinate plane, or input output, referring to the same thing. So a function, just like that line we would have graphed, okay, that's an example of a function. So we put in our input into our function and we get an output. So if we're looking at perimeter equals 4 times the side length, okay, well, whatever the side length is going to affect the perimeter. So side length would be our independent variable, our input. Our output would be our perimeter because it's dependent upon whatever the side length is. As the side length gets bigger, then correspondingly, the perimeter is getting larger. But then you see it goes up at a linear function, so it's not going to go up exponentially or anything like that. So the perimeter of an equilateral triangle where all three sides are the same is 3 times the length of one of its sides. You write an equation using P for perimeter and side length. Well, just like 4 times S, we would use 3 times the side length equals the perimeter. So P equals 3S. If we did our XY table, or in this case, it would be our S and P table, okay, then we would come up with different pairs. And obviously, if we have 0 for a side length, then we're going to have, if we had 0 for our side length, then we wouldn't have a perimeter because we wouldn't have a triangle. So 1, 2, 3, 4, and then the perimeter would be 3, 6, 9, 12. So it's still going up at a constant rate. It's going to be still linear. So we still have a function here. So this would be our formula. These would be 3 points that we could choose and go on from there. Again, usually if we're writing our own rule or we're talking about a function, we'll usually use x and y, because in a coordinate plane we have the x-axis and the y-axis, and then that tells us how much we're moving right or left of the origin or up or down from the origin. And in our calculator, that's the x and y pairs that we'll use in plotting points and finding rules. So I usually won't put it as S and P or anything like that. I'll keep it as X and Y. You'll see some like this where they say Xanos and Yolita or Xavier and Yolanda in this case. Again, I think they use the X and Y for the letters of the first name to help us think X and Y. Okay, but these two people are playing a game. When Xavier says a number, Yolanda performs an operation with Xavier's number and says the result. The table shows the four numbers. So 2, he says 2, she says 4. He says 3, she says 5. 4, 6, 5, 7. So whatever number he says, she's adding 2 to that number to get our output. So the input would be X, the number he says, the output, she's adding 2 to that number, and that's what we get as our dependent variable or output. So the rule would be y equals x plus 2. And as long as you kept doing that and doing it correctly, we could follow that pattern into infinity if we wanted. We could even have, obviously, negative numbers, sometimes not always in real world situations like the example of the triangle or the square. We can't have a negative side length, but down the road, we will be graphing negative numbers, and the same rules for functions apply for those as well. So, and then we have direct proportionality, which we've talked about last year, but just remember, if things are directly proportional, it goes through the origin, or 0, 0, and it's linear. So if it's linear but does not go through the origin, then it's not directly proportional. They're still related. We still have a function. It's just not direct proportionality. So this graph right here would be directly proportional because it goes through the origin, 0, 0, and it's linear. So it's got to meet those two criteria. If it goes through the origin, but then it has some weird U or J shape or something out here, okay, it goes through the origin, but it's not linear, so it's not directly proportional. Still is a function, and just not proportional. So let's look at an example of this. The area equals side squared. So this would be the area of a square. Okay, so if we multiply the side by side or do side squared, that gives us our area. So obviously, if the side is 0, we don't have an area. 1 squared is 1. 2 squared is 4. 3 squared is 9. So we look at the shape of this graph, and it's no longer linear. Still is a function. Okay, it's going to, if we were to show the second quadrant over here, it would look like a smiley face, and we'd have a parabola. Okay, but we're just looking at the first quadrant because, again, in this example, we can't have a negative side length. Okay, but we square our numbers and then we plot the different points. And for this example, it would be going up exponentially. So as we go up by 1, by 1, by 1, we're going up by 1, 3, 5. So it's going up at an accelerated rate. So it's still is a function, yes, but it's not directly proportional. Let's look at example 5. So if we graph y equals 1/2 x minus 2, y equals 1/2 x minus 2. So we have the standard form, which is ax plus by equals c, or we have mx plus b form, which is this form right here, where we have slope right here and then our y-intercept right here. This is linear, and the easiest thing to do for a line, since we only really need 2 points in order for it to be a line, let's plug in 0 for x. 1/2 times 0, 0 minus 2 is -2. Okay, then if we do, let's just plug in 1 for x. Or let's do, yeah, we can do 1, that's fine. No, let's do 2, sorry, just to make it a whole number. So 1/2 times 2, 1/2 times 2 is 2 over 2, which is just 1. So 1 minus 2 is -1. So we have 2 points. We could keep going. We could choose different values, but then we just need those 2 points to plot it. So 0, -2, I go over 0 and down 2. And then I go over 2 and down 1. And then we would just connect those dots. I don't have a ruler on me, so it's not very pretty, but we'd connect those dots, and then it would continue infinitely in both directions. Now, if it's a quadratic or something like that, we'll obviously need more than 2 points. But for a line, that's all we need. And this is linear, so that's all we would need. So, okay, graph 2 points, connect the dots. Make sure you draw your arrows indicating it goes on infinitely, and there is your linear function. Lesson 42, we're looking at volume. So most of these are on your reference sheet. We talked a lot about volume last year. So a volume of any prism, okay, where it's going up, it's not meeting at a point like a cone or a pyramid or something like that. The top surface and the bottom surface match. They're the same. What we can do is you can find the base. Okay, this isn't like base times height, the lowercase b, the uppercase b, I think it's the same thing on a reference sheet, indicates the area of the base times the height of the prism. So we have a rectangular prism right here. The rectangle on the bottom would be a 4 by 5 rectangle. 4 times 5 is 20 times a height of 3. Well, that would be 60. And then its volume, so it'd be 60 cubic, whatever these are. I don't think it gives us. Okay. But again, for you visual learners, I think, again, it becomes a lot more work doing it this way. But if you can visualize 4 across, 5 deep, and then 3 high, and then kind of count the cubes that you would have in there, the 1 by 1 by 1 cubes that would be in there, count up the total, that would also be your volume. But again, there's so many cubes that we can't even see that we got to kind of mentally account for. And again, counting up 60 of those versus just doing length times width times height, I think would be a lot easier. So base area of a rectangle, well, rectangle is length times width. So for a rectangular prism, it's just length times width times height. So these 3 numbers multiplied together. And again, since it's multiplication, we can do 3 times 5 times 4, 3 times 4 times 5, 4 times 5 times 3, it's all going to equal 60. So we can multiply in any order. If we remember base area times height, and for any prism, so if it was a cube or a triangular prism or a trapezoidal prism or octagonal prism or whatever it was, then we just find the area and multiply it by the height. That's going to give us our volume. Let's look at this. So we have a cube. It's 2 by 2 by 2. So we do length times width times height, or base area. 2 times 2 is 4 times 2 is 8. So 8 cubic feet. And since it's a cube and we know length, width, and height are all the same, we can just do side cubed, or side to the power of 3. So 2 cubed is 8, or we can do 2 times 2 times 2. It's also 8, same thing. And just make sure that we remember that our units, in this case feet, are cubic feet. We're talking about volume. We have 3 dimensions. That's why our units are raised to the power of 3. And then if we're looking at 57 pounds per cubic foot, what did the 2-foot cube weigh before it was carved? Well, if it's 57 pounds per cubic foot and we have 8 cubic feet, okay, we would do 8 times 57, and that would be 456 pounds. So a lot of times I'll do that with find the volume of a swimming pool to figure out how many gallons or how much weight or whatever it's going to take up, because it's filling up 3-dimensional space. So a lot of times we'll use that to figure out a volume of your garden planter or whatever. How much dirt is it going to take, and how many pounds of dirt is it going to take if you get so many cubic feet per pound or so many pounds per cubic foot. How much is it going to take you? So oftentimes we need to find the volume of some 3-dimensional shape in order to figure out how much of certain supplies that we're going to need. Okay, now this one looks a little different. So again, if we can re-visualize it as a 2-dimensional shape. So here we have 12, and that lines up with this one down here by 12. Then the 15, 15, 20, 20, and then we add 12 and 15 to get 27 on the back. So even though the 27 isn't indicated right here, we know based on, all of these are right angles. So that's got to be 27 and it's feet. So 27 feet in the back. So we would find the area of this, and we have 1, 2, 3, 4, 5, 6-sided shape. We could break it into 2 quadrilaterals, and we have a 12 by 12 square. 12 squared is 144 square feet. Then we have 27 by 20, which is 540 square feet. Add those together, we get 684 square feet. So that's our base area. Then we multiply by the height of 10 feet. So 684 square feet times 10 feet gives us 6,840 cubic feet. So again, that's where we want to find the base area. It's really nice when it's a triangle or rectangle or an easy shape to work with. That's not always going to be the case, but it's still a prism. And because this top shape right here is going to be exactly identical to the bottom shape, it's not coming to a point or getting skinny or anything like that. So we find the base area, multiply by the height, and we are done. Okay. And then surface area, this relates to 3-dimensional shapes as well. We have surface area, we also have lateral surface area, and then we have volume, which we just got done talking about. So surface area is, let's say we want to, wrap a present or something. We don't need enough wrapping paper to fill up the box. We just need enough wrapping paper to cover the box. So that would be surface area. Or if we want to paint the outside of our house, we're not going to paint, this concrete slab, or we're not going to paint the shingles on top of the roof. We're just going to paint the outer 4 walls. We would need to know lateral surface area. We don't need volume. We don't want to fill up our house with paint by any means. We don't want to, paint top and bottom, as we mentioned. We just want to paint the 4 walls on the outside. That would be lateral surface area. So in this one, the figure represents a cube with 10 centimeter edges. Find the total surface area of the cube. This is where I think we watched a video, or we will, about nets. We talked about them last year. If you guys are good at drawing those and kind of laying them out, imagine this is a box and you laid it out, you cut it up and laid it out 2-dimensionally, what it would look like. And then you could, find the area of all 6 shapes and then add them together. What's nice with a cube is we have 1, 2, 3, 4, 5, and 6 sides, just like a dice. We have 6 sides. So if we do 10 by 10, that's 100 square centimeters. We could do that 5 more times, but we know they're all going to be 100 100 square centimeters, and then we would add those together. So surface area is still area. We're still units squared. So we would do 6 times 100, so it would be 600 square centimeters. And if we wanted lateral surface area, it would be 1, 2, 3, and 4 sides, not the top or the bottom. So it'd be 4 times 100. So it'd be 400 square centimeters. So that's the difference between surface area and lateral surface area. And I think the formulas for total surface area and lateral surface area should be on your reference sheet. So again, as I said, if you're really good at drawing out the nets, that can help you visualize something that's 3-dimensional in 2 dimensions, and that's a little bit easier to work with. So we have dimensions of a cereal box, so estimate the surface area of the box. So estimate tells us we can round up or down. So we would have 8, 12, and then 3. So let me try and okay, so drawing 3-dimensional objects is sometimes tricky because you got to kind of make your mind see it 3-dimensionally. It's not always the easiest. So with the cereal box, and we can estimate, so that tells us we can round, and we're surface area. So 8, where'd you go? 8. It's 3. Okay, so if we were to think about this two-dimensionally, we'd have six sides. We would have two of these. Two of these, top and bottom. I'd have one more. I'm going to duplicate it. Another room. Okay, but if we were to divide it out into two dimensions, we would have 1, 2, 3, 4, 5, 6 sides. 1, 2, 3, 4, 5, 6 sides. It wasn't drawn very good, so I think it'd be easier just to look at it. So this one, we have 3 by 12, which is 3 times 12 is 36. And then we have two of those sides, so we can go ahead and multiply that by 2. So that'd be 72. Okay, this is 8 by 12. 8 times 12 is 96. 96 times 2 is 192. So we did the 3 by 12 and the 8 by 12. And we would have 3 by 8 for this bottom and top rectangle. 3 times 8 is 24. 24 plus 24 is 48. Okay, then I would add up all 6 sides, or since I knew opposite sides are the same measurement, I just multiplied by 2 to make life easier. It'd be 312, and what were our dimensions? Inches, so 312 square inches. Again, drawn out, as you saw, I wasn't the best at drawing it two-dimensionally. If you're really good at that, it's going to make life a lot easier. So you have the left and right side, the top and bottom, and then front and back. Again, imagine you just take that cereal box and you break it apart to where all the sides can just lay out flat on the table. Then you have a two-dimensional shape. Since it's still area, we're still looking at something two-dimensionally, even though it's a three-dimensional shape. We're still looking at area, but in this case, it's just of our 6 different sides. And we add them all up, and we get 312 square inches. Again, it's not volume, so it's not cubic inches. It's still square inches. Okay, practice set for those we'll go over when we be in class. That's all we have for today. We'll get to 44 down the road. So good job today, you guys. Keep up on your homework, keep up on these videos, and we'll go over in class. Thanks.